Hello, Algebra 1 students. Welcome back to videos on Topic 6, Exponents and Exponential Equations. Last class, in Lesson 6.6, we were introduced to how to graph a basic exponential equation. And so between that and your homework, you went through how to graph 2 to the x, 3 to the x, and 4 to the x. And you might remember that we started off class by folding a piece of paper and commenting that the number of layers based on the folds increased exponentially. So today we're going to go a little bit further into that topic. Our title for today is Exponential Growth and Decay, and of course we'll learn more about that as we go through. But let's begin with an opener. Opener-wise today, we are going to look at two separate questions. We are going to look at the problem 2 times 1/4 to the first power and compare it to 2 times 4 to the negative first. Now, you should be able to plug these into your calculator and get an answer, but you also equally should be able to do these by hand. So just to give you a hint before you get started, remember this just has all numbers in it, and whenever we evaluate an expression with only numbers, we do follow PEMDAS. So try to evaluate A and B, and then if you're feeling bold, answer C and D. Once you've attempted those, unpause the video and we'll go through them together. Ready, set, go. All right, so part A, we want to go through keeping PEMDAS in the back of our mind. I'm just going to work horizontally to the right here. We need to go through and follow PEMDAS. So the first thing with the P for parentheses, we look inside the parentheses and say, is there anything else inside the parentheses that's happening to the 1/4? And the answer is no. There's just a 1/4, nothing else going on inside the parentheses, so we're done. However, then we get to the exponents, and so it says 1/4 to the first power, not including the 2 yet, only the 1 is attached to the 1/4. But we should know at this point to do a number to the first power, it just means one of those numbers. So 1/4 to the first is 1/4. I'm done with the exponents. You also might notice that when I wrote the 1/4, I wrote the 2 so that it's in line with the 1 and not the 4. That way, when we move on to our multiplication here, we remember to multiply fractions. We need 2 different fractions, and so 2 is easily written as a fraction for 2 over 1. And now we multiply straight across. 2 over 4, and hopefully you remember back to elementary school to reduce 2/4 to 1/2. If you tried this on your calculator, you probably got 0.5, and hopefully you also know that that is the same as 1/2. All right, let's compare that to B. PEMDAS as well. We'll just write this up here so we have that nice reference. Nothing to do inside the parentheses. There's just a 4. Now we do the exponent. So we have 4 to the negative first. How do we tackle 4 to the negative first? Oh, that's right. We learned how to do this last class, or a few classes ago rather. We take that exact expression 4 to the negative first and move it to the other side of the fraction, in this case the bottom of the fraction, and make the exponent positive. So 4 to the negative first is 1 over 4 to the first. We still have exponents to do though. We need to do 4 to the first power, which is just 4. Now we're done. And oh wait, doesn't this look familiar? 2 times 1/4, that's what we had over here. And hopefully now we can see that this is 1/2 or 0.5. So part C was definitely a giveaway. Why are both answers the same? A lot of it has to do with that negative exponent, right? It was the same problem, just in disguise. 4 to the negative first is the same as 1/4. And once you realize that, it should be pretty easy to see that these are the exact same problem. So, thinking about what happened here, we had 4 to the negative first, and that negative power turned 4 into 1/4. Now, 4 is a number that is greater than 1, isn't it? 4 is larger than 1. Versus 1/4 is a number that is less than 1. Oops, less than 1. So my question on part D then is, if you do a number like 4 to the negative first power, will it always have an answer between 0 and 1? And let's look at a few examples, right? One example is the one we just saw. If B equals 4, then we get 4 to the negative first, which is 1/4. And this number is between 0 and 1, right? 1/4 is bigger than 0, smaller than 1. But what if I gave you an example of B equals 2/3? Well, if we do 2/3 to the negative first power, Remember, a negative power to any fraction is always going to flip the fraction, and this is just going to become positive 3/2. Is 3/2 between 0 and 1? Well, I think if you picture $3 and you split that in half, $3 split in half is 1.5, and that's not in between 0 and 1. So in fact, I don't think we can say that b to the negative first is always an answer between 0 and 1. Sometimes it is. If you start with a number bigger than 1 and do a negative power, it becomes between 0 and 1. But if you start with a number between 0 and 1 and flip it, it will become greater than 1. And that is pretty important for today. Okay, now let's back out of this weird mathematical discussion about exponents and let's move more into a little bit of a real-world situation. I know, shocking coming from math, right? So, last class we did see the number of layers that occur when folding a piece of paper grow exponentially, right? It went from 2 to 4 to 8 to 16. You were doubling every time, a common ratio of 2, which is indicative of exponential growth. So now let's think of a new scenario. And this time, let's think about a scenario where you're buying a new car, brand new car for $30,000. Now, generally, and this is kind of a weird exception these pandemic years, and we'll discuss that briefly at the end, generally it's suggested to not buy a new car, at least financially. And the reason why is in the car market, your new car's value is going to begin to decay. If we're talking about money, sometimes instead of decay, you'll hear the phrase depreciate. Right? Decay, depreciate. Depreciate is the opposite of appreciate. If you're in a good housing market, your house might appreciate in value. It increases in value. However, if you're in a car market, generally your car depreciates in value. Very few cars appreciate in value unless they're like a classic car, collector's item, something like that. In fact, and this is a true fact, the average car, the average brand new car, tends to lose 20% of its value per year for the first 5 years. That's a lot of value, right? To put that in perspective, if you paid $100 for your car in the first year, now your car will only be worth $80. Right? You lost a lot of money on that. And so that's suggested that you buy or you wait at least a year or two because that same new car that originally cost $30,000 is going to be a lot cheaper if you wait a year to buy it used. Now we can actually look at this as an exponential equation, and we'll discuss more about these exponential equations and writing them in a few lessons. But for now, if a car loses 20% of its value, and if you have an old version of this worksheet, you might have to change this, then what we say is there's 80% of the car's value left. That's why there's an 8 in here, and there is supposed to be an 8 in this equation. So our equation says f of t equals 30,000 times 0.8 to the t power. Down below, notice it tells you that t is going to be the number of years that you have the car, so this is like your time in years. And we're going to look at an equation c equals f of t, where c is, of course, the cost of the car after some number of years. Now, we are going to be using our calculators here. I certainly don't want to do 30,000 times 0.8 a bunch of times, so let's go ahead and look at this table we have down below. We have times of 0, 1, 2, 3, 4, 5, and we can see all those in the table. And we have outputs that are blank. This is where your calculator comes in, and I hope you're ready for it. In order to find the cost of this car after 0 years, and that actually means when you bought the car, then we need to take our equation, and we need to do 30,000 times 0.8 to the, and instead of t, notice that 0 is the t, so we're going to replace the t with 0. That's something you should be able to type into your calculator. And if you do that all correctly, you're going to end up with 30,000. Great. Well, why don't you guys go ahead and fill in the rest of this table using your calculator. Same idea. We'll check your results in just a second, and then we'll talk about graphing the table after. Ready, set, go. All right. Well, hopefully you filled in everything. If you want to see the right answers, I'm going to put them in right now. If you're not quite sure where these answers are coming from, you should definitely talk to your teacher or a classmate because you're probably just doing something wrong on your calculator. Okay. This last one, by the way, this $9,830 has a decimal at the end, and since we're dealing with money, I'll go two places out. None of the rest had cents tacked on. All right, so now we have this table, but we do want to actually see what this graph looks like. So you'll notice that the y-axis, the output, does not have any numbers on it. Well, we're going to fix that by putting our own numbers there. And I'm actually going to start with the highest value here, 30,000. 30,000 goes way up at the top. We can even graph that too if you'd like. This is the point 0, comma, 30,000, right? So 0, comma 30,000. First point. Whew. What about the rest, though? I mean, do we need to put every thousand up here? Do we need 30,000 tick marks? Well, hopefully not. Do we need 30 tick marks started at 1,000? That would probably be okay. But what if instead we just went through and just did a few of them? For example, halfway to 30,000, and I'm just approximating halfway right here, is 15,000. And then maybe you thought, well, instead of going by ones, couldn't we go by fives? And I think so. 15,000, here's going to be 20,000 and then 25,000. That's not too bad, right? Keeps our graph from getting too messy here. And I mentioned this last video, but the nice part about graphing is you don't have to be perfect. We're just going in an approximate spot. So here's going to be 5,000. And then we have, of course, 10,000 up here. And my tick marks are approximately spaced equally, right? This one is a little bit larger than the rest in terms of spaces, but oh well, not a big deal. Why don't you go ahead and graph those points with me, and we'll see how we do. My next one is the point 1, comma 24,000. 24,000 is just under this 25 mark, so maybe right about here. Okay. And so maybe you can do that quick math and realize that your car lost $6,000 worth of value in the first year. All right, let's do the next one. This one I'll do in yellow, 2, comma 19,200. So 19,000 is below 20,000, actually a little bit lower below than this guy was. And so this next year, if you can again do that quick math, it looks to me like we only lost about $4,800. So we didn't lose as much this time. And that's because we're doing percentages. First we did 80% of 30,000, that's our 6,000. Then we did 80% of 24,000. If you do a percentage of a smaller number, you're going to get a smaller answer. So we lose less and less value every year. All right, enough of that. Let's get our last couple points in. 3, comma 1530 is going to be right about at 15,000, isn't it? And then we have 4 at 1228. So 4, comma, that's right in the middle here. And then we finish off with 5, comma 9,800. That's pretty much 10,000. So we'll just go right here. So can you see that our spaces between consecutive points are decreasing? And it should decrease. Now, a couple things to note. First, if we had lost $6,000 every year, then our graph would look like that. It would be linear. All right, and it would tell us that after 5 years our car has no money left. It's worth 0. And if you buy a car that after 5 years is worth $0, then you've probably done something wrong. Instead, we should notice as we go through and connect these that we're actually starting to see a bit of a curve. And the curve gets a lot sharper after those first 5 years. We start to do something like this. That's our exponential curve showing the prices of our car after each year. And this is, again, a pretty accurate statement most years. I mentioned that in these pandemic years, it's probably not going to be quite as accurate. What's happening right now is because we can't produce as many new cars, people are turning to buying used cars. There's not as much inventory, and so people can charge more money for used cars, which means your car isn't going to lose value as quickly. Instead of losing maybe $6,000, maybe the first year it only loses something like this, and we end up with a little bit of a higher price in cars. Okay? So you should note that your car's value stops decreasing as rapidly after 5 years. We can see that in the graph. And by the way, this type of graph, although still exponential, is not the exponential growth that we saw last class. This type of graph is known as exponential decay. So in Algebra 1, you're going to be required to recognize two types of exponential functions, the two that we've just mentioned, exponential growth and exponential decay. As just with every new topic in math, we're going to try and look at those from four different perspectives. Today, we're going to look at them in three perspectives. Those perspectives are a graphical perspective, okay, a tabular perspective, so looking at numbers in tables, and then also looking at numbers in equations. And we're going to have to tell, based on the graph or the table or the equation, is our exponential function growth or decay. The fourth method is going to be using word problems, but we're going to get to that in our last two classes. So graphically, we actually already know what they look like. We've seen exponential growth before. Those looked like our folds in our paper, our layers, and we see that it starts small and grows very quickly. And exponential decay is what we just saw. That's where your price starts high or your numbers start high and then they decay down low. All right. You should notice that both of these never quite get to zero. At least this year, they're not going to get to zero at all. And that's pretty good. So let's go ahead and move on to our tabular recognition. Okay. We're going to decide which functions below are exponential growth, exponential decay, or neither exponential growth or decay. And we're going to justify our answers using that common ratio. Right? So why don't you go ahead and just focus on the outputs for now and see if you can find the pattern of each of the outputs, and then maybe digging back into knowledge from last class, decide if those patterns make our equation exponential or linear, and then going even further, is it growth or decay? Once you've tried these four, go ahead and unpause and we'll do a quick conclusion. Ready, set, go. All right. Well, let's look at all the patterns first, and then we'll try to analyze those. We look at patterns going from left to right. So I'm just going to work this way each time. And it looks like here we're multiplying by 2 every time. Versus the second one, I think we go up and we add by 2 for the outputs. Our third, there's a couple ways I think to look at this third one. First, there's a typo here. This should say 27, not 37. Whoops. First, you could maybe say, well, it doesn't look like it's multiplying. Isn't this actually just dividing by 3 every time? And you're right. There's nothing wrong with saying dividing by 3. You could also do division with multiplication. They're the same thing. And you might recognize that instead of dividing by 3, you could multiply by 1/3. A third of a number just divides it by 3. All right, and last but not least, this table might have thrown you off, especially going from 2/3 to 1. So if you ignore these two for now and don't cross them off, we'll come back to them, then just look at the patterns of these last three numbers. Even though they're fractions, oftentimes the numerators or tops of the fractions will have one pattern and the denominator will have another. And that should make it pretty apparent that we multiply the numerators by 3, the denominators by 2, and so if you think of that as a fraction, what we're really doing is just multiplying by 3 on the top over 2 in the denominator. 1 times 3/2 is 3/2. And maybe that makes a little bit of sense then if we multiply by 3/2 here. You can see we're doing 2/3 times its reciprocal, and we know when we multiply reciprocals the answer is always 1. Alright, so what does all of this find for us? Well, we learned last class if you can divide two consecutive numbers and get the same answer every time, then that demonstrates exponential behavior. So in this case, if I were to do 2 divided by 1, 4 divided by 2, so on and so forth, you get the same thing every time. I think we end up getting 2 every time. Or you could think whatever we're multiplying by, if it's constant, then it's going to show that this is exponential something. And because multiplying by 2 makes each number bigger, I bet we can say that this is exponential growth. And our common ratio is 2. You can put times 2 if you want. Second table, notice here we're adding every time. And in fact, because we're not multiplying or dividing, this table isn't exponential. I'm just going to cross that off. And we know that because there's no common ratio. Instead, there is a common difference. And the common difference is positive 2. This is an example of a linear function, right? We did those last semester. Third table, this is exponential. We're multiplying every time or dividing. If you divide consecutive numbers, you get 3. Okay, and this is exponential. What's happening to the outputs? It looks like to me they're decreasing in value, so I think this is exponential decay. And the common ratio is 1/3. We always talk the common ratio in terms of multiplication if it helps. Last but not least, this table is also exponential something. We know that the common ratio is 3/2. But then we have to ask ourselves, if you're multiplying by 3/2, are the outputs getting larger or smaller? Well, 3/2 as a decimal, we talked about this earlier, is 1.5. If you multiply numbers by 1, they stay the same. But if you multiply by 1.5 larger than 1, I think that will make the numbers grow larger. So this is exponential growth. In fact, as a conclusion for this page, if you have a sequence of numbers, like our outputs up above, that have a common ratio that is greater than 1, can you see those common ratios that are greater than 1 that we saw up here? These guys, right? Then the sequence shows exponential growth. However, if our sequence has a common ratio that's between 0 and 1, isn't 1/3 between 0 and 1, and we actually talked about this on the opener as well, it's all tying back together, then our sequence is going to demonstrate exponential decay. And that's because if you multiply by any number between 0 and 1, it decreases the value of your outputs. What are numbers between 0 and 1? Well, you have like 1/2, 1/3, 2/3. Right? We've seen those before. Okay, so I think we have a good idea of what graphs look like. Now we have an idea of what exponential growth and decay look like in tabular form. So why don't we finish off with our recognizing exponential growth and decay with if an equation is growth or decay just based on what the equation looks like. An exponential function at its most basic form has the format y equals b to the x power, where y is our output. Shouldn't surprise you then that x is the input, and b is actually a number. All right. In particular, and we wrote a couple equations before, if you're doing a number to the x power, that means you're doing a number times itself multiple times. Where have we seen numbers times itself multiple times? Well, isn't that just what happens here? We're doing 2 times 2 times 2 times 2, 2 times itself multiple times. And hopefully you're getting the idea, and you're going to be right here, that b is actually the common ratio. And so as soon as we know that b is the common ratio, we should, based on what we did for our tables on the previous page, be able to explain what values of b will cause our exponential function to decay or grow. And it's just like the previous page. If b, and I'm just going to draw an arrow over here, is a number between 0 and 1, what happens if you multiply by numbers between 0 and 1, like 1/2? Well, that's going to cause exponential decay. However, if b is a number larger than 1, like 2 or 10 or 1,000,000, and you multiply by 2 or 10 or 1,000,000, then that is going to cause our outputs to get larger, and so we say that's exponential growth. Well, knowing that then, let's make sure we can recognize when each of these equations demonstrate exponential decay or growth. There are 6 equations here. Be careful, there are a couple trick questions thrown in there. You really want to make sure that each equation is written in the form of y equals b to the positive x power. And once you've looked at the equation, you're going to identify the common ratio, that's b, isn't it? And then explain if the equation models exponential growth or decay. So take a couple minutes on these 6 questions. Once you're done, unpause and we'll see how you did. Good luck. All right, well, you're back, so let's look at the first problem and see if you're comfortable with it. Y equals 4 to the x power means you're going to put in some input, and then you're going to multiply 4 by itself that many times. If you multiply by 4, that means it's our common ratio, and multiplying by 4 increases the output, so that has got to be exponential growth, right? 4 is larger than 1. Second problem. 5/2 to the x, that's a fraction, that looks scary. It is going to be our common ratio, and if you multiply by a fraction, what does it do to a number? Well, hopefully you paused because there is no rule for that. Fractions can either make numbers get smaller if you multiply by 1/2 or 1/3, or they can make numbers get larger as well if this fraction is larger than 1. So I guess the question is 5/2 larger than 1? If you change it to a decimal, 5 split by 2, you get 2.5. And I'm pretty confident that 2.5 is larger than 1, which means this is actually exponential growth. Don't fall into the trap of assuming a fraction always means decay. It doesn't. Third one, 5/8 to the x power, common ratio. All right, but then 5/8 greater than 1, less than 1. Well, $5 split among 8 people, that to me sounds like it's going to be less than 1. This is decay. You could have also found that decimal. It's like 0.625, something like that. And it would also show you that that is less than 1. But now the real tricks begin. If on 4 you said the common ratio is 5/3, unfortunately you're not quite correct here. And that's because our equation isn't written in the form of y equals b to the positive x power. All right, it's disguising what the base is because of this negative. We need to remember that if you have a negative exponent, it gives you the reciprocal of your fraction to the x power. And so our common ratio is actually 3/5. 3/5 is less than 1, and so this is actually exponential decay. 2 to go. Okay. Y equals 2 to the negative x. Ooh, there's that negative, so don't assume the common ratio. We know this negative is going to take the 2 and rewrite it as 1 over 2, and we'll keep the x power on the outside. So our common ratio here is actually 1/2, and that is again exponential decay. Last but not least, a double whammy here, 1/3 to the negative 3x power. Well, we know that the negative is going to flip the fraction, so it becomes 3 to the 3x. And then we can also distribute this 3 out here and do 3 to the 3rd, which is 27 to the x power. 3 times 3 is 9, times the 3rd 3 is 27. And so our common ratio here is 27. And if you multiply by 27, I'm pretty confident your numbers grow, so that's got to be exponential growth. Okay, so we have learned today how to recognize if an equation is exponential growth or decay by looking at a graph, by looking at a table, and by looking at an equation. And that is our first of 2 main themes for today. But don't worry, our second theme is much quicker. We only have about maybe 10 minutes left. So let's tackle that, and then you guys can be done with lesson 6.7. The last part of today is going to discuss the average rate of change. Now, we haven't discussed average rate of change yet this year. So before we get into that, we're just going to start discussing the steepness of exponential graphs. We've discussed steepness before, right? Steepness, or in math we call that the slope or the rate of change, literally measures, it gives a number to how steep your graph is. For example, if you're asked to find the rate of change, which is a fancy way to say the slope, of this linear function down below, you should be able to do it. And let's do it together just so you remember. We pick 2 nice points, doesn't matter where they are, and we calculate the rise and the run. And so we can say the steepness or the slope of this graph is 2 over 1, or just 2 if you'd like. Could you do that with the exponential function? Go ahead, calculate how steep the exponential function is. Hopefully you got stuck somewhere along the way, because you'll notice that no matter where you were standing, here's my cute little stick figure, no matter where you're standing on this linear function, the steepness is exactly the same. However, if you look at individual points on this exponential growth function, over here, this point is not very steep, right? If you're standing on it, okay, it's pretty flat. But as you move to the right, what can you say about the steepness? Well, hopefully you're saying the steepness is getting more and more steep. It's increasing, something like that. And so it turns out that our linear functions, anything that makes a line, will have a constant slope. Anywhere you're on the line, it is the exact same steepness. But pretty much every other graph we study for most of the rest of your mathematical careers have different slopes depending on where you are on the graph. And so what we're going to not be able to do this year, and I'm going to put a little question mark here, is figure out how steep the graph is at a specific point. That's actually one of our main calculus concepts. And calculus is a class you can take in a couple years, right? This year's Algebra 1, then Geometry, then Algebra 2, then Pre-Calculus and Trig, and then Calculus. So it's a few years down the road. But if you stick it out, it's a really cool class. So again, it teaches you how to calculate the exact steepness at any point on a graph. But because we're not in calculus yet, we're not going to do that. Instead, we're just going to discuss, on average, how steep is a graph. Now, if we're going to talk about on average, maybe I were to just highlight this little segment here. Say, on average, how steep is that? Well, you'd probably take the steepness at the beginning, the steepness at the end, and you would average them, right? You'd add them up and divide by the 2 points there, and that'd give you an average steepness. And that is pretty much what the average rate of change tells us to do. The average rate of change, or the average steepness, is a concept we already know. We are going to pick 2 points, and we are going to find the rise and the run of the 2 points. This is realistically our slope formula, right? We've seen our y2 minus y1 divided by x2 minus x1. Okay. Now I wrote that in function notation over here. We're not really going to use this formula or even this one today. Today we're just going to focus on a graph and we're going to count the rise over run. Next class though, 6.8, we are going to actually use this formula and see how it's a little bit easier, especially if you don't have a graph. So how do we actually do this? Well, to find the average slope, we first need 2 points to count the rise and the run. That's why the average rate of change is always going to be given over an interval. For example, this interval that I highlighted before starts at an x value, can you see the x here, an x of 1, and then it ends at an x value of 2. So a problem might have said, what's the average rate of change from x equals 1 to x equals 2? So let's do a couple more actual concrete examples here so you can get the hang of it, and then that's it for the day. Find the average rate of change on the interval x equals 0 to x equals 2. Okay, well, we'll go back up to that graph, and we're going to find x equals 0 first. So we look at the x-axis. 0 is right in the middle, of course, but we don't put a point at 0, 0. We're talking about the graph. So when x is 0, we think about all the points on the y-axis. Every point here has an x of 0, 0, 2, 0, 3, 0, 4. But which one of these points do I actually care about? We care about the point that is on our exponential function, and that is this point right here. This is the point 0, 1, but it's also just the point when x equals 0. Then we are finishing our average rate of change at x equals 2. So we go along the x-axis over to 2 and say, okay, where on the graph, which of these points is on the actual function? Well, that's up here. This is an x of 2. How do we find the average steepness of this piece then? We just count. We count from 1 up to 4, so that's 1, 2, 3 up, and then we run over 2. And so the average rate of change, the average steepness of this graph is going to be the function, or the number, the steepness, the fraction, 3/2. And that's it. Okay, so I'm going to help you interpret 2, 3, and 4 first. You guys will try it, and then you'll check your answers with me right at the end. So what's the average rate of change on 0 to 1? Well, this means an x of 0, because it tells us x is between, and this means an x of 1. Find the points on the graph, calculate the rise and run. Average rate of change on 0, 3. We've seen this notation before. This notation doesn't mean the point 0, 3. This notation is telling us on the x-axis. If they ever give you an interval, you always assume it's the x's. And it's telling you on the x-axis, begin at an x of 0 and end at an x of 3. We've used that notation for domain and range before, haven't we? X of 0 to an x of 3. And so same thing over here. We are going from an x of 1 to an x of 3. So go ahead and apply those same concepts to the exponential graph up above. Once you've found your answers, check with me to make sure you've done it correctly, and you will have conquered this lesson. All right, you're back to check your work. Let's see how you did. X equals 0 to x equals 1. This is on B right now. So we're going to get rid of this just to make sure things are easy. X equals 0 to x equals 1. Our rate of change, I think, isn't bad. Up 1 over 1, right? Easy enough. So this will be 1 over 1. Or if you wanted to simplify it, it is just 1. The next one goes from 0 to 3. Okay, there's 0, there's 3. Ooh, it's way up there, isn't it? Oof. Okay, and so that's x equals 3. We went to 3 on the x-axis, and then we count. Yep, we go up from 1 to 8, I think, is a rise of 7, and then we go over 3. So this is going to give us an average rate of change of 7 over 3. Last but not least, from 1 to 3. All right, we're going to change this guy right here, and we're going to go from x equals 1 all the way up to x equals 3. So we rise from 2 to 8, that's up 6, and then over 2. And so on average, the graph increases up 6 over 2, or if you reduce, that's just a steepness of 3. It should probably make sense that 3 is our most steep portion out of all of these, because from 1 to 3 is the steepest part of the graph. From 0 to 3, it's a little less steep there. The number is going to be a little bit smaller. So thank you for hanging out with me. As always, we did two things today. We discussed the average rate of change, but we only did it with graphs. Next class, you'll use tables and equations. And then we also talked about how to decide if a graph shows exponential growth or decay, looking at graphs, tables, and equations. Good luck on your homework tonight and your knowledge check next class. And I'm excited to teach you about lesson 6.8 next time.